Hey, everybody. I hope you can hear me and see me effectively. I do apologize. I wish I had gotten this video out to you, or at least posted last night. That's my fault. I will be gracious on timing and assignments. I'm not sure there's an assignment that I'm posting with this one, but I will be much more consistent and ready to go as we hit next week. I've had some interactions with you via the via email, and that's been good. I will tell you this: we are going to be setting up a schedule where we're going to have some actual live Zoom interactions in classes. And so, actually, keep this in mind. Monday at 9 o'clock, I'll be sending you an invite. I might try to get it to you in a couple of different ways, possibly by email or actually having the link to it on the LMS. I think that might be good to try and keep us daily going to the LMS to make sure that we're doing and working on the things that we need to do. I'm excited to actually interact with you, in some face-to-face ways. I've found that even though I kind of think I'm a hermit sometimes, I'm really not. I do crave being able to interact with people. I hope you are getting good interaction with friends and family, not out and about, because we should be limiting that connection and our access and touching people. I want to post, really just share a little bit of an idea with you. If we are Christians and we claim to love people and to seek what's best for them, then in this time, in this health crisis, isolating ourselves from people and not touching them and not coughing on them is actually what is most loving and what is best for them. I know that that can seem kind of hard, uh, but thankfully, in this world of technology, we can connect by sending some messages, or we can connect via live Zoom. So I'm looking forward to doing that with you guys. I know that there's ways that we can set up. There's things we can do to be encouraging to people. Send notes, send text messages. I think that would be important. Connect with people, connect with your family. So what I wanted to do is I wanted to connect with you today via this message and talk about thermal energy transfer. We're getting into our physics lesson now. Our lesson is going to be on the concept of conduction. So I am going to share my screen, and hopefully the large talking head of Mr. Hicks will go away. You'll be able to see some things on the screen, but I'm also going to try a whiteboard option here. I'm recording this via Zoom, and we're going to talk. Hopefully you'll have some paper available so you can take some notes as we talk. But I do have a note page with some basic stuff and some images that I've already shared it with you. I'm going to put the link to it in the LMS, and so you'll be able to look at that and gain access to that. I'm going to try and keep things condensed and in a concise location for these lessons, so you're seeing the video, you're seeing all the other links, and not having to scroll through 1700 different things. So we're going to talk about thermal energy transfer. We introduced this earlier. We understand the concept that energy has uses. And the interesting thing is that energy can move, it can flow, it can go from one place to another, and it's actually always seeming to do that. It's always moving from one place to another. Electricity, we've learned this: you have stored up electricity in a capacitor, and you connect that capacitor to a circuit, and it's completed. Boom! It starts moving. It moves from high to low. Thermal energy moves from high to low. Uh, Gravitational energy, gravitational potential energy, it starts moving from high to low. Think about the water that's up high in a mountain. It starts flowing downward from high energy, and it converts, of course, to kinetic energy. But then the potential energy is, becoming lower. It's always going from high to low in that case. It's a natural thing, natural flow, high to low. It's actually a law of thermodynamics that energy moves from high to low. I use the example of water and gravitational potential energy because we've had a lot of water. You know, I want to put this out there, this little sidebar, and I hope that I can exhibit this in real life, but I really do try. Uh, you know, many times we get upset. Oh man, more rain, can't go outside, can't do stuff. I try not to have an attitude where, oh man, it's raining, what am I going to do? Sometimes I just go out in the rain and get wet because there's nothing you can do about it. But God sends rain for a reason. He sends rain to replenish the earth, to do all sorts of wonderful things in nature, you know, give us fresh drinking water, make the plants grow. I don't know about you, but I'm enjoying the fact that spring is happening. I was outside playing with my kids yesterday, and my daughter's tree, she's got a tree. We planted it in her honor, I guess you could say, when she was born. It's already starting to bud, these beautiful pink flowers. Don't laugh at me. I love the beautiful pink flowers on that tree. It's just wonderful. God made a beautiful world, and we get to live in it. So that rain is essential for that. One thing to think about: it's springtime, pollen is coming, and guess what? The rain knocks the pollen out of the sky, hopefully keeping the allergies and the craziness down a little bit. I'm actually going to try and change that. Oh, that's actually better. Okay, I think that's better. Sorry. You know, I'm still working things out in my home office here. I hope you guys are setting up a good situation for yourselves to make this work. So let's get jumping into thermal energy and thermal energy transfer. I've already mentioned a few things, but I'm going to share the screen to, let's see, to right here. This page. Nope, that's not it. Stop sharing screen. Sharing screen to, okay. It is giving me trouble. I apologize for this. I'm clicking on the right thing to share screen, and it is not doing it. I'm going to share screen to the whiteboard. We're going to go for it. I hope you guys are seeing a whiteboard, full size. Right. I'm going to just put some notes in here. We're going to talk about thermal energy transfer. There are actually three methods of thermal energy transfer. They are conduction, convection, radiation. Conduction, convection, and radiation. I hope you guys can see that. I wonder if I can change the format. There we go. I made it darker there. So we're going to start off talking about conduction today. That's about all we're going to get into. I don't see the need to cram it all in here. We could try to jam all three of these in at once, but let's let it marinate and solidify. So conduction is essentially thermal energy transfer from high to low, and that's an important sidebar here. I'm gonna make that known here. Is as you look at the note sheet, which I was hoping to show you, but my screen share wasn't working quite right. The note page actually that I've made up actually has a notation that the second law of thermodynamics tells us that energy transfers from high to low. So essentially, every single one of these is a definition that is partially going to have the same wording as the second law of thermodynamics. So thermal energy transfer from high to low, mostly through solids and involving direct contact. Now, technically, this could happen with a solid and a liquid. This is actually kind of interesting. Now, please understand, I am not telling you to go and practice any of these things. because I don't know if you have oven, stove privileges, and of course, messing around with these things and making a mistake can cause houses to burn down. Right? That would not be good. But if you were to take a piece of metal and make it really, really, really hot, you could do this with a marshmallow poker. My kids have been begging to have a bonfire. We've got marshmallow pokers. You could jam a marshmallow poker into a fire and let that thing heat up hotter and hotter and hotter and hotter, even close to red hot, and then put it into a glass of cold water, and the thermal energy will transfer from the hot, high energy metal poker into the water. Now, what's really cool is if you were to do that, you could actually see so much energy transfer into the water through that direct contact that it could actually heat up the water and boil some of it. You could actually possibly see some turn into steam, right? But that's because of the direct contact. And really, it's essentially molecule to molecule, right? Molecule to molecule. One molecule gets hot, then it slams into another, slams into another, slams into another molecule, and it gets hotter and hotter and hotter, and it goes down the line through conduction. Now, you may have experienced this if you've done any cooking. You may have experienced it by leaving a metal utensil leaning on the edge of a pan, and you come back 2 minutes later as the food has been simmering or cooking, and you grab the metal utensil and it's hot. That's because the end of the metal utensil is in the hot container, the pot, and there's a part of it leaning on the edge, which is hot, and then the thermal energy transfers up the device from molecule to molecule to molecule, and then you grab it and your hand feels that thermal energy. Essentially, that's thermal energy conducted to your hand. So that conduction to your hand hurts because your hand is low energy and that's high energy, and it burns you. So you've got thermal energy transfer from high to low, mostly through solid direct contact, but it can also be solid in liquids in contact, and even solids and gases in contact. Solids and gases in contact are harder to kind of visualize because gases are, again, a fluid that is constantly flowing and constantly moving. And so a gas molecule might come in contact with something, but it keeps flying away. And so it's really kind of hard to visualize it. It's also hard to understand how much thermal energy was actually transferred to those microscopic, tiny air molecules. So let's continue on here, and let's talk about a little connection here to specific heat capacity. Objects with a low CSP are typically going to be called conductors. And what that means is they actually are going to absorb thermal energy quickly and transfer it very, very quickly. I believe we mentioned this in other videos, is that objects with a low specific heat capacity are things like metals, right? A metal fork, a marshmallow poker. Those objects have a low specific heat capacity, so when they get hit with thermal energy, you put them in a fire, they start to absorb that thermal energy very, very, very quickly. They get hot fast. But then, right, when you grab them or they touch something, they start to conduct that thermal energy away very, very quickly as well. I think I used the example of putting a piece of aluminum foil around a potato. You cook a potato in aluminum foil and you bake it in the oven. It's, the potato and the aluminum foil are like 350 degrees hot. You take the aluminum foil off real quick, let it sit for 2, 3, 4 seconds, and you can crumple it up in a ball and it won't hurt your hand because it's off the potato, it's thin, it's got a low CSP, it has dumped its thermal energy from high to low into the air, into whatever it's touching, and then your hand is fine, right? So that's low specific heat capacity. Those are what we would call conductors. So now if we're thinking about high CSP objects, those would be what we call insulators. Something with a high CSP would be something like a piece of wood. It's much higher than a piece of metal. It doesn't absorb thermal energy as quickly, and it doesn't transfer thermal energy as quickly, But here's the one really unique thing about it is that these objects with high specific heat capacity, they typically are going to be holding much more thermal energy than other objects, right? They just have this capacity to hold onto it. It's like every pocket or every bag has a certain capacity. Well, their backpack is just bigger. It has the ability to hold more books, more energy, right, in that backpack. So a great example of this is water. Right, water. I know we're talking conduction, and conductors and insulators, and I talked about solids, and now I'm moving to water. But water is just such a great example. Water has a high specific heat capacity. It has the ability to absorb lots of energy, and it might take a while for that to happen, but it absorbs a lot of it. But it also holds onto it. This is why water is so great. Water, when it gets hot, holds that thermal energy for a very long time, and it doesn't radiate, but it convects that thermal energy out over a longer period of time and runs convection, okay? And this is huge. We're gonna get into this when we talk about convection and radiation. I think that's our next lesson, convection and radiation. But I think we're going to handle that live on Monday. So that's going to be great. I'm really looking forward to connecting with you guys about convection and radiation on Monday. And I just love the concept of convection. If I had to think about which three, conduction, convection, radiation, are my favorite, I think I would go with convection. Convection runs the whole planet, right? It's awesome. Although radiation's cool. All right, I'm getting off topic here. But the concept of water having such a high specific heat capacity, it holds it very, very well. So it may not conduct as well as a solid. It insulates better, but that's the way we need to remember this. Another substance that has a high CSP and is an insulator, but we'll go to solid here, is something like insulation. It's a material that does not conduct thermal energy very, very quickly. Now, places where you might experience this, there are plenty of them. You can very well experience this when you get out of the shower, right? When you get out of the shower or the bathtub next time you take a bath, what I want you to do is put 1 foot on a bath mat and 1 foot on a tile floor, right? You will feel a difference. Right? The bath mat has a high CSP. It's an insulator, so it doesn't conduct thermal energy away from your foot very well. A tile floor has a lower CSP, and so when you step on it, when you get out of the shower, you feel much colder because it's conducting that thermal energy out of your body. Because guess what? Your body is 98.6 degrees. Your house is probably somewhere around 70. So you are high, your house is low. Thermal energy leaves you, goes to the house, high to low. Right? So that's why your feet will feel something different. A place you can feel this. I don't recommend doing it, but you know what? Jump in and help cook, right? You're at home, we're sequestered, we're quarantined, we're spending time with family. Spend some time helping cook. And you can actually experience this. I don't recommend it with a metal cooking utensil, right? You can experience the conduction by leaving a metal cooking utensil sitting on the edge of a pot, and the thermal energy will transfer. And then you'd grab it and it would get hot, right? Don't do it because I don't want you to get burned. But that's where you could experience it. Here's an interesting thing you could experience it. Have a bonfire with your family, right? And get a marshmallow poker and put a marshmallow, on the end of the marshmallow poker, but put the marshmallow poker in the fire, but leave the marshmallow outside the fire. So the thermal energy, all right, so think of it. Fire is where my finger is. I'm sorry, this is so terrible. I would draw this on the board if we were in class, or I'd get a picture of it. But put the fire here, the marshmallow here, and the thermal energy will transfer this way, and will start to melt the marshmallow. Actually, here's another way you can do this. Get permission to do this because again, it's the stove, right? It's the stove and heating up something. But what you could do is get something on the stove that's cooking and put a metal utensil in it, but leave the handle draped off the edge. And you know what? Get a little bit of wax. Get a little bit of wax and put it on the end that's not in the hot pot. And what you'll find is you'll find the thermal energy transferring down. If here's the hot area, you'll find the thermal energy transferring down and melting the wax, right? You'll find it melt the wax. It might take some time for the thermal energy to get there, but it will get there. Now, there's a couple things that are going to affect the rate of conduction, because every material has a different conductiveness. So what's going to affect the conduction is the actual nature of the material. Very possibly even the density of the material. Another thing that could affect it is the shape or the dimensions. I think I spelled dimensions right there. The shape or dimensions of the material. That will affect the conduction. Something that's got a very thin shape to it versus something that's got a very thick shape to it will actually will conduct differently. Sorry, I got distracted there for a second by a phone call. So all those are going to have an effect. Something like the length. An object that's really, really long is not going to conduct as quickly as something that's as short, because it doesn't have as far to go. So those are some influencers of the rate of conduction. I'm going to stop sharing this screen now, and I'm going to see if I can get that note page back up. And that's not it. I think this is it. So here's some basic notes that I've basically talked through. And here are some examples that are visual examples of what we've talked about. This last one I really wanted to put on here because this one is kind of talking about the rate. This is an illustration of the rate of conduction. If we had something that's heating up right here, heating up this, call it a metal bar. Well, this area that's right near the heat source is going to heat up the quickest. And then the further away you go, you actually have less temperature involved, less energy, because it's got to transfer that length, right? And there's going to be a certain rate of getting from closer to further away. So I hope that makes sense to you. As we continue on, we're going to talk about convection and radiation in our next lesson. Continuing on this understanding of the movement of thermal energy, I'm really excited about convection, because it's actually something that powers our whole world. Here we're going to have like a little introduction to essentially meteorology, some global physics, and so I will try to make sure that is engaging for you. I don't know if you like the weather. You should be paying attention to it, because if we're stuck inside because of a lot of rain, we're going to want to get outside when it gets nice. And that's what I'm hoping to do here this afternoon. So I hope you guys are having a good day. Please don't hesitate to contact me if you need something. I'm glad to do it. Glad to help. I'm going to stop sharing this screen, and I'm going to stop recording, and I'm going to sign off. This is Fizz Hicks. Hope you're having a good day. Sorry I didn't wear my tie for this lesson, but I decided to go casual. Have a good one. See you later.